Alright, for problem A, logarithm 10 to the power. If you just write 2x, you will see what happens. Window -10 to 10, 1, -10 to 10. Graph, you will see this not straight, but if you go to, if you insert, second insert a parentheses, delete, not that one. Let's say second insert parentheses, and then insert another parentheses, and I need to plug it in here, the 10 to the power, second insert. Okay, and my window is okay. Let's graph, and now you will see it's a straight line. Alright, so the way you're putting in your log terms in the calculator is very important. Here you want the 2x as a quantity to be the power of 10. That's the reason I inserted another parentheses. And algebraically, if I look at A, y is equal to log 10 to the power 2x. And then this is equal to 2x will come down as a coefficient. And this is equal to 2x because log has a base 10 and the power, so the answer is the power 2x times 1, which is 2x. So you will see that you have the straight line y is equal to 2x. Now if y is equal to 2x, if the value is 0, you know, y is 2 times 0, which is 0. If x is 1, y is equal to 2 times 1, which is 2. So to make sure your graph is correct, you can find the value of y at x equals 1. Let's see, then if I go second calc, 1 value, enter. Let's say I want x equals 1, it should give me a 2. So then I did correct. Okay, so part B, this is a subtraction, so I'm going to write it as a ratio, which is logarithm 2, which is just a horizontal line because logs of numbers basically represent a number. So then if I put it in my calculator, let's see how I'm going to put that in. So log 2x, close it, and then minus log x, close, and graph. Now because of like if it's so close, you see, so then if you go to window, let's make y from, let's say, -1 to 1 with 0.05 increments. Graph. Okay, so let's keep playing with it. So I want, oh, y max, I want 1, 0.05, and then graph. Okay. Now you will see here that um, it's a horizontal line, correct? Log 2 is a horizontal line at that value. And we only have the positive side uh, of the graph, this side, not to the left, because x values of logs are not defined. So C log 10x squared is x squared log 10 and 1, correct? Log has base 10, so this is equal to 1. So it's y is equal to x squared. Let's look at our graphing calculators. Clear, clear. I'm going to say log and 10 to the power x squared, close. So I'm expecting to see a parabola here. And let's look at negative 10, 1. So then let's look at here negative 10 to 10, increments of 1. As you see, I end up with a parabola. All right. Now, it's a quadratic. Now, let's look at D. Y is equal to 10 to the power log x squared. This is equal to, because the bases are the same, x squared. And here you need to ignore the fact that the function is undefined at x equals 0, because log 0 is undefined. Just ignore the fact, and you will see when you graph it, it will be in the quadratic form. Clear? Y? Clear? So I'm going to write it as, this is D, right? Okay. 10, let's go it up a little bit. 10 to the power, open the parentheses, log, open the parentheses, x, um, don't open it again, delete, okay, x square, close, and close. And then see what happens when the window and then graph. You will see it's a quadratic again. All right, let's move on to problem 4. The population of Kenya is growing exponentially. Its population was 23.3 million in 1988. So let's assume t is equal to 0 in 1988. And so when it is 0, the population was 23.3 million. And in 1995, 7 years after, which is 1995, so 7 years after, the population was 28.3. All right. using this point, which let's say population is p sub 0 c to the power t. 28.3, original is 23.3, c to the power in 7 years. So 28.8 over 23.3 is c to the 7. C is equal to 7th power of 28.8 divided by 23.3. And this will be approximately 1.02816. So the model for, to answer A, the model for Kenya's population is equal to P, my original, times my growth factor to the power T, where it is where time is measured in years after 1988. And what will be the population in 2005? B, 2005 is 17 years after 1988. So then population will be 1.02816 to the power 17. So let me do this calculation. 1.02816 to the power 17, and then you multiply by 23.3. 37.4 approximately a million. C, use logarithms to find the doubling time. Basically 23 times 2 is 46.6. 23.3, 1.02816 to the power t. If I divide both sides, it will be always 2 because I'm doubling it, 1.02816 t. So from here, log 2 is equal to t log 1.02816. So t is equal to here log 2 over log 1.02816. And that will be approximately 25 years. Next question is 6. The best company earned 50 million in 2000. So let t be the number of years after 2000. So it was 50 million with a rate of 2%. If the rate is 2%, then I add 1.02 to find the growth factor, 1.02. So then the income for best company is 50, my growth rate to the power t. And then the income of the other company earned 30 million with 1.065 to the power t, because 6.5% is 0.065, and I'm going to add 1.065. So these are my models. When will company A overtake company B in annual income? Let's make them equal to each other. So zeros are gone. So 5/3 is equal to 1.065 to the power t, 1.02 to the power t. And I can write this as 5/3 1.065 over 1.02 to the power t. Then I'm going to take the log of both sides. So t comes down. Then I'm going to end up with t is equal to log 5/3 log 1.065 over 1.02. So my answer will be approximately 11.83 years, or by 2012, if I add that to 2000. Approximately 12 years, obviously. Okay. Next question. Problem 10. The half-life is given as 5,330 years. If the level of carbon-14 radioactivity in charcoal in the cave is approximately 14% of that of living wood, estimate the date when the paintings were made. So starting from P sub 0, let's see here, um, oops, P sub 0, if it is 14%, then 0.14 to the power t, and so 1/2 P sub 0 is the half time. These are gone. It's 0.5, 0.14 to the power t. So log of 0.5 is t log 0.14, and t is equal to log of 0.5 over log of 0.14, which is approximately 2.8365 half-lives, which is, if you multiply that by 5,730, you should be able to see 16,253 years. And last question. So this is a decay problem. If 40% remains after 10 years, then you can find the model for the quantity remaining after t years by solving, let's say r sub 0, c to the is 10 years, 10. So then 0.40 r sub 0 is r sub 0 c to the 10. So 0.40 is c to the 10. So the log of 0.40 is 10 log of c. Oops, not this method, sorry. Because c is in the variable is in the base, I'm going to say c is 10 to root of 0.40, which is approximately 0.91244. So my model is r initial 0.91244 to the power t. That is for A. For B, how much will be present after 25 years? So then R is equal to R sub 0 0.91244 to the power 25. So which is equal to, if I take this, if I do this calculation, I'll end up with 0.1011 R sub 0. So that means about 10.11% of the initial amount will be present after 25 years. C. What is the half-life of the substance? That will be, you know, R0 over 2 equals R0, 0.91244 to the power time. Obviously these are gone. This one half, which is 0.5, is equal to 0.91244 t. So log 0.5 is t log 0.91244. T is equal to log 0.5 log 0.91244, and the answer will be approximately 7.56 years. Alright, I'm gonna work on D. We're on the same page here. How long will it be before only 2% of the original amount is left? So 0.0 t original amount r sub 0 0.91244 to the power t. So log of 0.2 t log 0.91244. So t is equal to log 0.2 over log 0.91244, and my answer for this question will be approximately 42.7 years. Hope this helps. I'll see you next video. Thank you.